Okay, hello everyone. Today we will learn properties of point estimation part 4. We will cover Rao-Blackwell theorem and MVUE, minimum variance unbiased estimator. Okay. Chapter 9.5 is about the Rao-Blackwell theorem and minimum variance unbiased estimator. And this Rao-Blackwell theorem is very important theorem to proving minimum variance unbiased estimator. So the theorem 9.5, the Rao-Blackwell theorem. Let zeta hat be an unbiased estimator for zeta, such that variance of zeta hat is less than infinity, and if u is a sufficient statistic for zeta, and if we define our zeta hat star as conditional expectation, expected value of zeta hat given u, then for all zeta, the expected value of zeta hat star is again zeta, so it is an unbiased estimator for zeta, and variance of zeta hat star is smaller than variance of zeta hat. So what it says is that if you have an unbiased estimator zeta hat, and if you know the sufficient statistic u, if you define a new estimator which is zeta hat star, if you define this one as the conditional expectation of zeta hat given u, then you will going to have the lower variance. So your new proposed statistic, which is zeta star, it will have lower variance than the original statistic, which is zeta hat. Okay, so let's prove this theorem. For the first one, we were going to prove this one first, which is we were going to use theorem 5.14 and 5.15. So theorem 5.14 is expected value of the definition of zeta star is this thing, and the double expectation of this thing is expected value of zeta hat, and since zeta hat is unbiased estimator, this is zeta. So we proved the first thing, and what about second thing? We can apply the theorem 5.15 here. So to calculate variance of zeta hat star, we will calculate expected value of variance of zeta hat. Expected value of variance of zeta hat given u plus variance of expected value of zeta hat given u. You can write it this way using theorem 5.15, and from here, as we know, the expected value of zeta hat given u, this is our zeta hat star, and so and here the variance of zeta hat given u, the variance of this thing should be greater than 0, since this is variance. And so so this one shows that the variance of zeta hat is greater than or equal to variance of zeta hat star. This part is zeta star. Okay, so we proved second one, and yeah, so this is the proof for the theorem 9.5. This theorem 9.5 implies that an unbiased estimator for zeta with a small variance can be made to be a function of a sufficient statistic. What it means is that if we have unbiased estimator for zeta, and if we have sufficient statistic u, then we can improve it using zeta hat star. So if we can improve our estimator zeta hat by using conditional expectation given the sufficient statistic. And as we know, the conditional expectation, this thing, is a function of sufficient statistic. So we can write it as HU, and by the theorem 9.5, we know that this HU have less variance. So this zeta hat star variance of zeta hat star have smaller variance than the original zeta hat. Okay, and actually this zeta hat star with completeness condition, this is minimum variance unbiased estimator, and that's the by applying Lehmann-Scheffé's theorem. But in the textbook, it didn't fully describe about completeness and the Lehmann-Scheffé theorem. So I will briefly introduce this concept and move on to the examples. So here is Lehmann-Scheffé's theorem. Let U is complete and sufficient statistic. And actually, I didn't explain what is complete means, but I will intuitively explain it. Let me just give you the theorem for now. If expected value of HU is G zeta, and then HU is uniformly minimum variance unbiased estimator for G zeta. This is easily proved by the theorem 9.5 that we just explained. So the variance of HU is less than or equal to variance of the original estimate. Let's say zeta hat, I don't know, G zeta hat is the estimate for G zeta. So G zeta hat is an estimator, then G zeta hat. Yeah. So yeah, H of U. This is another estimate for G zeta, and it will have minimum variance. And the other thing that we need to prove is that there should be other estimators. So there should be different versions, like expected value of G zeta hat 2. Again, this is also expected value of G zeta. So this is the first one. We have two estimators. We have two unbiased estimators. So the first unbiased estimator for G zeta is G zeta 1, and the second unbiased estimator is G zeta 2. And what if we define our HU1 as expected value of G zeta 1 hat given U, and also let's define H2U equals expected value of G zeta 2 hat given U. Okay, then these two H1U and H2U are expected value conditional expectation given sufficient statistic. So the variance of this thing and this thing, they both are less than the original one. So variance of H1 of U is less than or equal to this thing, and also variance of H2 of U is less than or this thing. So, and actually it can be uniquely described. So actually if you define this way, then H1U and H2U should be the same. And actually this part can be proved by the property of completeness. And so for now, I will skip the concept, what is the complete statistic, and rigorous proof for this part. but probably you can learn this theorem if you go to graduate level mathematical statistics course. In the textbook, it didn't describe about Lehmann-Scheffé theorem and also completeness, and so I will just briefly give you some kind of insight what is completeness and what is Lehmann-Scheffé theorem. Yeah, that's it. So let's move on. Okay, let's move on to example 9.6. Let y1, y2, yn denote a random sample from a distribution where probability of yi equals 1 is p and probability of yi equals 0 is 1 minus p, which is the Bernoulli distribution. So y follows Bernoulli p, and use the factorization criterion to find a sufficient statistic that best summarizes the data given MVUE for P. Okay, so use the factorization criterion. So to use factorization criterion, we firstly need to calculate the likelihood. So what is the likelihood of y1 to yn of P? Then this is probability of y1, joint probability of y1 to yn, and actually the p of y, probability of y, can be described as p to y and 1 minus p to 1 minus y. Why is it? So if y is 1, then probability, so here this one is 1 if y is 1, p, and 1 minus p if y is 0. So you can find that if you write your probability as this thing, then if y is 1, then the probability of y is p, and if y is 0, then probability is 1 minus p. So and since y1 to yn are independent, the joint distribution of y1 to yn can be written as p to sum of yi, and 1 minus p to n minus sum of yi. Okay, and so this is our likelihood function, and for this one we can write it as this part is our g sum of yi comma p and times 1, and this one part is our h of y1 to yn. And by factorization theorem, this sum of yi, sum of I equals 1 to n yi, this is sufficient statistic, for theta, for p, and what else? And we want to find the MVUE for P, and so we need a unbiased estimator for P, and we know that y bar, which is sum of yi divided by n, then this is unbiased estimator because the expected value of y bar is p. So this is unbiased estimator, and actually this one is function of sufficient statistic. So we can say this is g of our unbiased, our sufficient statistic. So this is the function of our unbiased, the function of sufficient statistic. So this y bar is UMVV. This y bar is MVUE. MVUE. Okay. Let's move on to example 9.7. Suppose that y1, y2, and yn denote a random sample from Wavelet density function given by here, and find MVUE for zeta. And to find an MVUE for zeta, we need a sufficient statistic U, and we need so firstly we need sufficient statistic. Statistic. Firstly, we need sufficient statistic. Second, we need an unbiased estimator. Zeta hat. Oh, no. Function of u. Yeah, function of u. We need function of u, and that is unbiased estimator. And expected value of f of u is zeta. And then the f of u is MVUE. Okay, so firstly, let's find sufficient statistic. To calculate sufficient statistic, let me calculate data likelihood first. So likelihood of zeta, this is f of y1 to yn, and since y1 to yn are independent, this is zeta nth to nth, and it y1 times y2 times, so yi equals to 1 to n, and e to the minus sum of yi square I equals 1 to n, and divide by zeta. And from here we can check that this part is g of sum of yi square comma zeta, and this part is h of y1 to yn. So by using the factorization theorem, we can check that this one is a sufficient statistic. Sum of yi square is a sufficient statistic. Okay, and the next thing is we want to find let's say this is u, function of u that is unbiased estimator for zeta. So before we do that, we want to calculate expected value of u, and probably we can apply some function to make this expectation as zeta. Probably we can find the function later. So what is expected value of u? Then that is expected value of sum of yi square, and before we calculate this, what is expected value of yi square? And so let's try to solve what is expected value of yi square first. So from previous slide, expected value of y square is its integration from 0 to infinity. So 2y zeta, so y square 2y zeta e to the minus y square divided by zeta dy. And so this is from 0 to infinity, zeta 2y third and e to the minus y square over zeta dy. And actually this integration, it's difficult to solve for because of this part. So probably one option is let's define w is y square, and let's use change of variable. Then y is square root of w, or w 1 over 2. And so then this is integration from 0 to infinity theta 2 w 2/3 and e to the minus w over theta, and this part it's dy dw times dw. So what is dy dw? Dy, so differentiate this one, which is 1 over 2 w minus 1 over 2. So put it here, and then what we will get is from 0 to infinity, 2 is cancelled, 1 over theta, and we have 1 w, and e to the minus w over theta dw. And actually this is this part plus this part, that's exponential distribution. So this part is actually exponential distribution with parameter theta, and the whole equation is calculating expected value of exponential distribution. So this integration, the result of this integration is theta, because if w follows exponential distribution with parameter theta, then expected value of w is theta. So ey square is theta, and then probably it's easy to find the function of unbiased function of sufficient statistics. Then what it is, so our sufficient statistic is sum of yi square, and we know that expected value of this thing is n theta. So this is n number of yi squares, independent. Yi's are independent. So we can do, what we can do is that expected value of sum of yi squared divided by n should be theta, and so this one should be our UMVU, uniformly MVUE, actually MVUE. Okay, so this is our MVUE, and this is end of the solution. Okay, let's move on to example 9.8. Suppose y1, y2, yn denote a random sample from a normal distribution with unknown mean mu and variance sigma square. Find the MVUE for mu and sigma square. So now this time we have two parameters, mu and sigma square, and as we already solved, to find MVUE, firstly we need to find sufficient statistic for mu and sigma square. So to do that, the likelihood of mu and sigma square, this is joint distribution of y1 to yn, and this is actually 1 over sigma square root of 2 pi nth, and exponential 1 over minus 2 sigma square, sum of I equals 1 to n yi minus mu square. Okay, so we are multiplying n number of FYIs, and we will get this thing as our likelihood. And if we rewrite this thing as 1 over sigma square root of 2 pi nth and exponential this part 1 over minus 2 sigma square. For this part, we can rewrite it as sigma I equals 1 to n yi square. So this part is yi square minus 2 yi mu plus mu square. So this part can be rewritten as minus mu sigma I equals 1 to n yi plus n mu square. Okay, so we can rewrite this as this. And what's next? Here we can see that this part is function of sum of yi square comma sum of yi and mu and sigma square, and this is function of these two and our parameter theta, and this part is our h of y1 to yn. And so by factorization theorem, sum of yi square, so sum of yi square and sum of yi, they are jointly sufficient statistic for mu and sigma square. Okay, and so and what we know is that y bar is unbiased estimator for mu, and also we know that s square, expected value of s square is sigma square. And so, and actually this y bar is function of sum of yi. Y bar is sum of yi divided by n, so it is function of sum of yi, and also s square is 1 over n minus 1, sum of I equals 1 to n yi minus y bar squared. And actually this one we can rewrite it as 1 over n minus 1 sum of yi square I equals 1 to n minus n y bar square. We can rewrite this way, and so this is function of so this s square is also function of sufficient statistics, sum of yi and sum of yi square. So this y bar and s square, they are y bar and s square, and they are MVUE. Y bar and s square are MVUE. Okay. Let's move on to example 9.9. Let y1, y2, yn denote a random sample from the exponential density function given by here. So this is exponential distribution with parameter theta, and find an MVUE of variance of yi, and variance of yi is theta square. Okay, so before we do that, we want to find a sufficient statistic for theta. So let's move on by calculating likelihood function. Likelihood function is f of y1 to yn, and since they are independent, we multiply the density functions, which is 1 over theta nth and exp minus sum of yi divided by zeta. And from here, we can write this part is our g of sum of yi comma zeta, and this part is h of y1 to yn. And so by factorization theorem, this sum of yi, the sum of yi is our sufficient statistic. Sufficient statistic. Okay, and as we know, the expected value of y bar is zeta, unbiased estimator for zeta. So why don't we try expected value of y bar square? So y bar is a function of sufficient statistic, and also y bar square is function of sufficient statistic. So let's try to solve expected value of y bar square. And actually this is variance of y bar plus expected value of y bar square. From when we are calculating variance of something, it is expected value of squared of that variable minus the expected value of that variable squared. So from that formula we can write this way, and variance of y bar is n over zeta square over n, and expected value of y bar is zeta, so its square is zeta square, and so this is n plus 1 zeta square. Okay, and from here, so expected value of y bar square is biased estimator for zeta square. So to make it unbiased, we multiply this term like this way, n over n plus 1 y bar square. Then this should be zeta square. Okay. So this one is unbiased estimator for zeta square, and also this one is a function of sufficient statistic sum of yi. So n over n plus 1 y bar square is MVUE. Let's move on to example 9.10. The following data with measurement in hundreds of hours represent the length of life of 10 identical electronic components operating in a guidance control system for missiles. The length of life of a component of this type is assumed to follow a Wavelet distribution with density function given here, and use the data to construct 95% of confidence interval for zeta. And when we are calculating confidence interval for zeta, the important thing would be use the statistic that have minimum variance, so that we can construct the narrower confidence interval. Because if we use the MVU, if we use MVUE estimate to construct confidence interval, the variance of that is smaller than the variance is smaller. So what that means is that the confidence interval is narrower. So let us firstly find the MVUE for zeta, UE for zeta, and actually we already found it from the previous example. For the Wavelet distribution, MVUE for zeta was yi square, sum of yi square divided by n. So this was our MVUE for zeta, and also previously we calculated that yi square y square follows exponential distribution with zeta for the Weber distribution, and if y follows Weber distribution, Weber zeta, and the yi square will follow exponential distribution of zeta, and also we want to use the known distribution that can be easy to find probability, and the other thing to note is that the exponential distribution with zeta 2 is actually equal to chi-square distribution. So one useful thing to know is that exponential distribution with zeta equals 2 is same as chi-square distribution with 2 degrees of freedom. So what we want to do is that y square follows exponential zeta, then y square divided by zeta times 2. This will follow exponential distribution with parameter with 2, and so this one is actually chi-square distribution with degrees of freedom 2. So this is what we were going to use, and to prove that let's say y square, let's say this is w, and if w follows exponential distribution zeta, then f of w y, let's say w, f of w is 1 over zeta e to the minus w over zeta, and then if we define our t as w over zeta times 2, then the ft is fw, and from here w is zeta t over 2, zeta t over 2, and here dw dt, and dw dt is differentiate this thing with respect to t, which is zeta over 2. So this is zeta over 2, and so you will get so this one is 1 over zeta e to the minus zeta t over t, zeta cancelled, and here 2 zeta over 2 zeta cancelled, and this is so 1 over 2 e to the minus t over 2. So we can show that this one t, and actually this is t, this is our t, follows exponential distribution with parameter 2, and that is actually chi-square distribution with parameter 2. You can check it from the density, and that exponential 2 is same as chi-square 2. And let's construct confidence interval using pivotal method in next slide. So so far we define our t is y square over zeta times 2, and this is following chi-square distribution with degrees of freedom 2. And actually we know that our sufficient statistic is sum of yi square. So let us use sum of y square over zeta times 2, and and then this will follow. This is sum of chi-square distributions of degrees of freedom 2. So 2 times and I equals 1 to 10. We have 10 observations, and so this thing will follow chi-square distribution with degrees of freedom 20. And so we can calculate the probability of uh, the probability of our given statistic I equals 1 to 10 yi squared b equals we are calculating 95% of confidence interval, and also we know that this one follows chi-square distribution with degrees of freedom 10, and let's assign 0.05 over 2% of probability this side, and 0.05 over 2 probability on this side. And to do that, we can use our R command to find the value for A and B. So the value A is 9.59. So A is 9.59, and our B is 34.17. And what's next? And you can create the confidence interval for theta. So from now, theta over sum of yi square 2 is 1 over 34.17, 1 over 9.59. And what is sum of okay, and if you calculate sum of yi squares from the data, this is 24.643, and so your confidence interval for theta is 24.643 over 2 times 34.17, and is less than 2 times 9.59 to 24.643. So this is our confidence interval, and if you calculate the first value and second value, you can find it. This is 1.442 and 5.139. Okay, so this is our confidence interval. Homework for chapter 9.5 are these. Okay, thank you very much for attending the class, and this week we have learned Rao-Blackwell theorem and MVUE, and I think the material is getting harder and harder, so probably you may have a lot of questions. So if you have any concepts that you cannot understand, please feel free to email me. I will explain more using 문의 게시판, question answer bulletin board. So hope everyone is doing well in the class, and also in this week you are going to have Thanksgiving Day, Korean Thanksgiving Day. So hope everyone stay very well. But yeah, probably because of the COVID-19, I'm not sure whether you can enjoy it. But I hope everyone enjoy our Thanksgiving. Okay, thank you, and see you next week.